Once upon a time, a wise man named Isaac Newton told us, "I can calculate the motion of heavenly bodies, but not the madness of people." He had discovered something so powerful yet so mysterious that it affects every piece of matter in the universe, from the smallest pebble to the largest planet. This force, called gravity, pulls everything toward everything else. It's everywhere, even though we don't always notice it. Imagine this. As you walk down the street, gravity is quietly working between you and the person passing by. It's even there between you and the coins jingling in your pocket. But because gravity is such a weak force, we don't feel these small pulls. It might not seem so weak, though, when you think about how difficult it is to jump more than a meter into the air before gravity pulls you right back down. Yet, believe it or not, gravity is actually quite feeble. For example, if you hold your arm out straight, even the immense gravitational pull of the entire Earth, countless quadrillions of tons, can't force your arm down. Still, gravity has a unique power. The more matter there is, the stronger it becomes. While it doesn't do much when you're holding a coin or walking by someone on the street, gravity becomes incredibly important for huge things like planets, stars, and galaxies. But when does gravity really start to matter? If we look at atoms, we see that the tiniest building blocks of the universe are held apart by the repulsion between their negatively charged electrons. This keeps matter solid and stiff. In the case of hydrogen, the simplest atom, gravity is about 10,000 billion times weaker than the force keeping its electrons in place. It takes more than 10 atoms before gravity wins over these other forces. Imagine a rocky world, around 600 kilometers wide, or an icy body about 400 kilometers across. If an object is bigger than this, gravity becomes the boss, pulling everything into the most compact form, a perfect sphere. That's why, in our solar system, large objects like planets are round, while smaller ones are shaped like lumpy potatoes. Now, let's go back to the 1600s. In England, a scientist named William Gilbert played with magnetic stones and noticed something strange. The heavier the magnet, the stronger its pull on pieces of iron. He also discovered that the pull worked both ways. The magnet pulled the iron, and the iron pulled the magnet. Gilbert wondered if maybe magnetism was the secret force that held the solar system together. However, another brilliant mind named Robert Hooke soon realized this couldn't be true. After all, heat makes things lose their magnetism, and the sun, as we know, is very, very hot. But Hooke was still intrigued by the idea of an invisible force like magnetism that could stretch across space and affect distant objects. Maybe, just maybe, gravity worked in the same way. The story of gravity continued with a mathematician named Johannes Kepler, who spent years studying the movement of the planets. After much hard work, he figured out 3 rules that explained how the planets dance around the sun. One of his most important discoveries was that planets move faster when they're closer to the sun and slower when they're farther away. Kepler described this by saying that an imaginary line between a planet and the sun sweeps out equal areas in equal times. Before Kepler, people thought that planets needed some kind of force pushing them along their paths, like angels blowing on them with their wings. But Newton, inspired by Kepler's work, had a different idea. He realized that the planets didn't need to be pushed at all. Instead, they were simply following their natural tendency to keep moving, something we now call inertia. Newton's first law of motion says it best. A body stays at rest or moves at a constant speed in a straight line unless acted upon by a force. But Newton wasn't done. He wanted to understand the true nature of gravity. He wondered, what if the force that pulls an apple from a tree is the same force that keeps the moon in orbit around the Earth? This idea was revolutionary because it challenged the belief that the heavens were governed by different laws than Earth. So Newton set out to measure how gravity weakens as distance increases. He compared how fast the apple fell to how the moon falls toward the Earth as it orbits, and from this, he discovered that gravity follows an inverse square law. That means if you move 2 objects twice as far apart, the gravity between them becomes 4 times weaker. Newton didn't stop there. He also proved that this gravitational pull, which follows an inverse square law, explains why planets move in elliptical orbits. Imagine slicing through a cone. Depending on how you cut it, the shape you see could be an ellipse, like a planet's orbit, a parabola, or a hyperbola. If a planet doesn't have enough speed, it stays trapped in an elliptical orbit around the sun. But if it has just the right amount of energy, it could escape forever, tracing a hyperbola as it flies off into the stars. With his law of gravity in hand, Newton could explain much more than just planetary motion. He also unlocked the mystery of ocean tides. You see, the tides are not caused directly by gravity, but by differences in gravity. The moon pulls on the earth, but the water at the seabed feels less of that pull than the water at the surface, creating a bulge in the ocean. As the earth spins, this bulge moves, causing the water levels to rise and fall along the shorelines. There's another tide, too, on the opposite side of the earth, where the ocean is stretched by similar forces. And because the moon orbits the earth as the earth rotates, the timing of these tides shifts by about 53 minutes each day. Newton also discovered that the tides caused by the moon are twice as strong as those caused by the sun. This led him to the surprising conclusion that the moon must be twice as dense as the sun, a remarkable insight. But Newton's journey didn't end with the moon and tides. His ideas laid the groundwork for future scientists like Einstein, who would later refine the understanding of gravity. Einstein discovered that gravity isn't just about mass, but also about energy. Close to the sun, for example, the gravitational field itself holds energy, making gravity slightly stronger than Newton had predicted. Even with all of this knowledge, gravity still holds many mysteries. For instance, near black holes and at the moment of the Big Bang, gravity breaks down into what physicists call a singularity, where the laws of physics no longer make sense. Scientists today believe that a quantum theory of gravity will one day solve this puzzle. Some researchers even think that all the forces of nature, gravity, electromagnetism, and the rest, are different faces of a single superforce. The only framework that hints at how gravity might fit into this grand theory is string theory, which imagines the universe made of tiny vibrating strings. In this strange world of 10-dimensional space-time, gravity might be leaking into extra dimensions, making it appear weaker in our familiar 3-dimensional universe. And so, the story of gravity continues, pulling us toward new discoveries, just as it pulls the planets around the sun.